talk about some recent development in combinatorics that have been mixing up different domains of mathematics. So I think it's interesting to have an overlook about it, because I think when you're young, you think that things are separated somehow. People things that don't mix up, and that's not true. So what I've seen that you have already have something about enumerative combinatorics. I will just mention a enumerative problem. So let's consider an example when you count, in which you count things. For instance, you count the partition of a set of cardinality n. Okay, so you for each n you have a number bn, which is an integer, and you want to see what happens with these numbers, how they grow, which is their complexity. And so you consider generating series, for instance, and that's what you get. It grows very, very quickly, because it partitions, and doesn't mean partitioning two sets, but you may partition it in many sets. So the number of possibility grows quite fast, and you get this series. And so what can you do? It's difficult to handle it like that. But it turns out that the series satisfy an easy functional equation, which is this one. So it's very compact, and somehow it hides the complexity of the generating series. And then in 2003, Clauser proved the following theorem. So I'm going to explain what the symbols and the words appearing in the statement. So this series B of t is not the solution of an algebraic differential equation with coefficient in this field here. Do you see the? Yes. Okay. So first of all, this field here, what is that? Well, this field is the following things. You consider series which are convergent and have a pole at 0, so you pull out the origin of the disk and have certain radius of analyticity around, but you don't fix the radius. So when you have a finite number of those series, they always exist on a common smaller disk. So it makes sense to add them, to multiply them. You can do all the algebra you want, and it works well. So those are series which has a pole at 0. They are convergent in a small disk, which on which we don't want to be precise. So that's the field, and then there's an algebraic differential equation. Something is going to pop up in the talk. So an algebraic differential equation is a differential equation as you imagine it. And the functional is a polynomial. That's what means algebraic. So you have a polynomial in t0, tn as a variable, and you evaluate it in the derivative of the function. Okay, so algebraic stands for the fact that the differential equation is associated with a polynomial. Okay, so that's a recent, relatively recent. Maybe some of you were not born, but a relatively recent statement, and it's somehow an instance of a general state of mind. When you count something, you have this generated series. Sometimes even the effect of counting, it gives you a functional equation, because you count them, look at the step n-1, and you see what happens each time you add a step. This gives you a functional equation, and then you exploit the functional equation to study the complexity of the series. In this case, well, you know that the series is not solution of a differential equation. It makes it a little bit exceptional anyway, because, there are many series that are not solution of a differential equation, but we are in a state of mind frequently of the idea that it's relatively common, let's say like that. So this is a general, as I say, a general pattern, and usually people when they look at this series, they try to classify the complexity. So they can be a rational function. Well, I got the wrong arrow. They can be algebraic function. It means that they are defined as implicit function of a polynomial. That's the step a little bit more complex. Or, I keep eating the wrong arrow. Or they can be what is called definite. It means that they are solution of a linear differential equation with rational coefficient. So the linear differential equation we have been seen in the first calculus classes. Or there can be what is called the algebraic series. The algebraic is short for differentially algebraic. It means that they are solution of an algebraic differential equation. Or, if none of those situation is verified, they are differentially transcendental. They are not solution of a differential equation. So people, when they count things, they try to classify this generating series and see in which of these classes, which are contain one into another, which of these classes apply to those generating series. So this question goes back somehow to what is called the Hölder theorems on gamma function, and so it has a long story. So the gamma function is, maybe you are acquainted with it. Gamma function was introduced by Euler in the 18th century. He defined it using an infinite product, but I prefer to use it using to define it using a theorem. So it is a meromorphic function over C, but if you look at it as a function of the real numbers, I mean the positive real numbers, is the only function who has the following properties. So, well, it satisfies this functional equation, gamma of t plus 1, it's equal to t times gamma of t. Gamma 1 is equal to 1. So you may immediately, I got the wrong chalk. You can immediately see that gamma of n is equal n minus 1 factorial. And now something worth noticing happen. If you add the differential equation, you have an initial starting point condition. You would already have your solution if everything is analytic or meromorphic and everything works well. This is not true in this framework, because if you find the solution, you can multiply it by any one periodic function, and you get another solution. So it's a little bit more complicated than in the differential case. And this theorem gives another condition to pick exactly the gamma function, and if you compose it with the logarithm, is complex. Anyhow, it's a function that interpolates the factorials, and it pops up in mathematics in many different domains of mathematics. And it turns out that it's not a solution of an algebraic differential equation with a rational coefficient. And it's a very old and famous theorem which has been proven in so many different ways along history. I mean, it's maybe one of the theorems which has more proofs in history, maybe. And so it has been the first theorem considering this kind of problem. And well, if you look at Hölder, maybe you don't speak German, I don't speak German, but if you look at the older article, the original article, one of the first formulas that you see is this one. Instead of considering the gamma function, you consider its logarithmic derivative, so gamma prime over gamma. And it's if you apply the derivation, the logarithmic derivation to the functional equation, which is up here, okay? Well, you see that taking the logarithmic derivatives, so the logarithm and the derivatives, you end up with this these functional equations here. Okay. So this functional equation is much more useful than the original one for the gamma function. And why is that? Well, it has the same shape, so to say, of the functional equation we haven't seen before. It's an order 1 functional equation with an inhomogeneous term. The other one was this one. Okay. So somewhat they look a little bit alike, and they are much easier to handle. And actually, this older theorem on the gamma function and the theorem by Clauser that I mentioned before, they are not completely independent. They are a little bit linked. There's a hidden link between the two. And the link is the following, is that if you take z to be the inverse of gamma of 1 over t, then you see that the functional equation of the gamma function becomes this functional equations here. Okay. Well, and of course, this is the homogeneous functional equation associated with this term. You know, it's just this piece here. So there's a link between the Clauser theorem we have seen at the beginning and the older theorem. Although Clauser did not use this property, but there's a link. And the link is that we know that this gamma function is differentially transcendental, is not solution of a differential equation, but the solutions of this functional equation here are given by one specific solution plus all the vector space of the homogeneous equation. It's like for differential equation. I mean, it's exactly the same situation. So somehow there's a link between the gamma function and the generating series of Bell numbers that we have seen before. And as I said, Clauser did not use this property to prove the differential transcendency of Bell numbers generating series, but I hope to be able to do so until the end of the talk, before the end of the talk. And so that's a little bit sort of a guiding line of what was happening. And before going into more technical part of the talk, I would like to give you another example of the same kind of ideas. And this example is the Ishizakigogawara Theorem. So you pick a Q to be a complex number, which is not 0 and not a root of unity. You consider two rational functions, and the solution of a functional equation, you see the shape of the functional equation is always the same. Okay, so order 1 with a non-homogeneous term. Well, it turns out that either this formal power series, Laurent series, this formal Laurent series is the Taylor expansion of a rational function, or it's differentially transcendental over COT, so it's not solution of an algebraic differential equation as before. So it's kind of a leitmotif. It comes in the I have too many things on my ear, sorry. Comes out. And so it's something bumping up in history somehow. And this Ishizakigogawara theorem have been used recently to enumerate lattice walk with small steps. What does it mean? It means that you take this quarter plane, and then you have the point with integer coordinates, and then you set you choose a set of steps which is allowed, and it's a subset of this vector like that. And so you have a walk at each iteration. So suppose you have chosen this and this as possible steps. You start at zeros, you go up, and then you go on the other way. Then you may decide to keep going, then to go up, and so on and so forth. And you can move only using the subset of steps you have chosen, okay? And you may want to know how many of this walk you can construct in this way. So you define the number of walk. You can define this Q of S, E, G, N. It's the number of walk which goes from 0, from the origin, 0, 0, to a point E, I, J, with n, using exactly n steps, okay? And so this is an integer number, a positive integer number. And then, well, no surprise, you consider a trivariate generating series with this coefficient. Oh, it turns out that, of course, these things satisfy a functional equation, which is a little bit complicated, and there are many different kinds, and then you can reduce them by symmetries and so on and so forth. In the end, there are 78 most important cases that are to whom you can reduce by manipulation. And there are five of them that have been studied using the Ishizakigogawara Theorem, and are these ones. And it turns out that after some manipulation, you can prove that the generating series here satisfies equidifference equations like the one in Ishizakigogawara Theorem. And so, well, it has been proved that Q of S, x, y, t is d transcendental with respect to the derivation in x and y and y, sorry. When t is a transcendental number between 0 and 1. It is differentially transcendental when respect to the derivation in t. This is even a more recent result, and more recently, Aline Bossan proved that even for some algebraic number, for t in some algebraic, taking some algebraic values, the series are still differentially transcendentals in x and y. Okay, so this is a small part of this of a whole topic of research. I mean, there are many people working on this topic, but we know almost all, I think, now about the differential properties of this generating series, but in particular, those cases have been proved using this theorem by Ishizakigogawara. And then, even more recently, Adamczewski, Dreyfus, Hellman proved another theorem which generalizes the previous one. So you take a formal Laurent power series which satisfy a linear functional equation of order n. So the coefficient are rational function, okay, and tau is a functional equation, is a functional operator, which is one of the following. It may be this operator that we have seen in the Claussard theorem, okay. It can be a Q-difference operator with Q non-zero and not a root of unity, or it can be what is called a Mahler operator. So the t is elevated to an integer power m, okay? So if you are in one of these cases, then either f, it's a rational function in a root of t, okay? Or it's differentially transcendental over the rational number. So there is a very strong dichotomy here, so it's a very recent theorem. And it applies to many situations in combinatorics. So to prove this theorem, for instance, if you want to prove it when tau is these things here, you have to use the Ishizakigogawara theorem in the sense that it's proved by recurrence induction on n. So you start via n equal 1 and you keep going. And so the step 0 of the theorem, it's a theorem you have seen before. Of course, Ishizakigogawara have proven this theorem by elementary techniques, and so they are a little bit limited when the size of the equation grows. And what makes the difference between this theorem we have seen here and the previous one, it was called difference Galois theory. So it's Galois theory for the ones which are already in Master 2, they know Galois theory. There's a Galois theory which follows a little bit the structure of the usual Galois theory that you learn during your Master 1. But it's done, it's studied, it's constructed for functional equations. And that makes the difference between the two proofs, and that's why they managed to prove a much stronger theorem, because they have more sophisticated means. So I'm going to speak a little bit about, what time is it? Okay. I'm going to speak a little bit about, sorry. Okay. I'm going to speak a little bit about Galois theory of functional equation. So there are going to be 3 or 4 slides, which may be a little bit tougher. But never mind, then you just need to remember the statement in the last of just 4 slides. So if you get a little bit lost, it's not a big deal. I mean, you shouldn't be lost until the end of the talk, even if you find that this part is a little bit complicated. So, what's the setting? The setting is the following. You start with a field, okay, of characteristic 0. You don't want to go into complication. And you have an operator on this field, which is an automorphism of the field. It respects sums, product, inverse, everything. Okay, and then you have the constant, which are the elements of the field that are left invariant by tau, and we suppose they are algebraically closed. It's a little bit, I mean, it's a very important assumption, but not at this stage. And then you suppose that this field also come equipped with a derivative, which commutes to tau. So just to make an example, to reconnect to the previous slides, an example could be the following. You take K to be the field of formal Laurent power series. You take tau to be this operator here that you have been seeing already twice, maybe. And then the constants are the constant that you imagine. I mean, the invariant element of the field are the real constant C. And if you want to find a derivation which commutes to the operator tau, well, that is t squared d over dt. So this is the situation of the first slides in the Clauser theorem. And I'm going to make a remark, is that tau leaves invariant rational function and convergent series with a pole at 0. So it stabilizes this field inside the formal Laurent power series on one side. And another things that I have been suggesting already, but I haven't been saying it clearly, is that tau acts in this way on the inverse of t, which is the link between the generating series of Bell's number and the gamma function. Okay, so this is the situation. You have this field with an automorphism which acts on the element of the field. Of course, is your function field, is a field of coefficient. You have some constant, and you have the derivative. So now you consider a linear difference equation with respect to the operator tau. What does it mean? It means that you consider an equation like this, tau of a vector y. It's equal to a matrix A times a vector. So A, it's a square matrix, is invertible, which is invertible, and y is your vector on a known function. Okay, so it's like a linear differential equation, but apart of the fact that you don't have derivatives but an automorphism. And then you construct by brute force somehow, I mean, you construct a sort of playground. You have this functional equation here, I don't know, maybe like so if you're, yes, A and B and C of t, so this is the example we are going to use later. So you have this functional equation here. You don't know if you have real solution. I mean, if you can find solution that can be really written like honest function. But you do something totally abstract. You construct an abstract playground where you can do whatever you want. You can find solution, take their derivatives, you do whatever you need to do. And this is called a delta Picavesi ring. It's like a splitting ring for splitting fields for the one who have already done Galois theory in there. And so this, it's an algebraic algebra R, where you find your solution. It comes equipped with an extension of tau, an extension of the derivative. The commutation between the two is preserved. And then in this algebra, you can find a matrix of solution, which is invertible, so it's maximal size of a matrix of solution. And somehow this algebra is optimal. It means that doesn't have too many things. It's in many sense optimal. So optimal means for one that it's just generated by the entries of y and their derivatives. So just what you need to do, you need your solution and you need to take their derivatives. And then there's a little bit technical property, which means that you haven't been adding some noisy things what may give you false information. I'm not going to comment on this. And this R is so optimal. I mean, one of the signs that your algebra is optimal is that you have not been adding constant, for instance. You could be adding useless constant in the theory, which may create some noise. You don't. And so, in particular, you have a small algebra where you can find a matrix of solution of your things, your system up here. So this is maybe a little bit scary, but it's just an algebra where you can do what you want. Should not be scary actually. So once you have this algebra, you consider the group, the Galois group of this functional equation. And what is that? Well, it's the following things. You take some automorphism from your ring R to your ring R, such that, well, it's written on the slide, when you consider the automorphism induced on your base field K, well, that's the identity. Okay, and of course it commutes to tau. You see it's here. It commutes to tau. What's the point of considering this? Well, you have your system here. So imagine you apply this phi to left and right. Okay, so you have phi here and phi here. Well, here they commute. Okay. The matrix A has coefficient in K, so it's invariant by phi. Phi is the identity of K, so this doesn't move. And you have Y here. So phi transforms a matrix of solution in another matrix of solution. And, well, you may guess or not, but it really works like a differential equation. It means that, So I should put the -1 in the right place. Well, if you take tau of this, it's equal to phi y minus 1, a minus 1, a y. Okay, so it's a so this matrix is left invariant by tau, and this means that it belongs to GL nu of the constant. Okay, it's like for differential equation. If you have a linear differential equation with the matrix linear differential system, if you have two matrices of solution, this one and this one, which are both invertible, you can obtain one from the other by multiplying by a constant matrix, and this is exactly the same thing. And what happens is that you have actually a morphism of group from the Galois group to the matrices. Okay, just as that's what we have written here. To any phi, you can associate this matrix with constant coefficient. So now I put the theorem in, well, because it's not a real theorem, it's like gesticulating. But, well, if the image of the Galois group here into the matrix here, it's small, it means that you have many relations among the solution. You can find many polynomials which annihilate in all the entries of y's. So that's what it means. So if you want to say it in a cultivated manner, I say, well, the Galois group is an algebraic subgroup of GL nu C. It means that it's a variety, it's a set of zero of some polynomials plus some other condition. That's one thing. And the other thing, it means that the dimension of this Galois group, it's equal to the transcendance degree over 0 over k. So you can find as many algebraic independent solution as the dimension of the group. And another important property, and if you have already seen some Galois theory, you will acknowledge that this is the starting point of the Galois correspondence, is that if an element over 0 is left invariant by all the elements of the group, then it belongs to the base field. Okay? So whatever is left invariant by the group, it belongs to your starting field of function. So what do you do? For instance, with this equation here, you start with tau of y equal y plus b, and b is an element of k. You construct your algebra R, which is obtained by adding to k a solution of the functional equation and all its derivatives. And what happens? Well, you can apply the derivative to this to the functional equation. For instance, you have tau y equal y plus b, and you apply your derivative on both sides, okay? And you get another equation. For the derivative of y, they commute. Remember that they commute. I call it y, sorry. W. So you can take the derivative of this functional equation as many times as you want. So, and you have all these functional equations that have all the same shapes, and you can find the solution in this algebra Rn. And you can consider now the Galois group of all this system here. What happens? Well, you take an element of the Galois group, and it must send a solution into a solution. And you see well, shall I erase a little bit? So you have tau y is equal to y plus b. Okay? And phi of y, w, sorry. Phi of w, it must be a solution of this equation. Okay? But the solution of this kind of equation is an affine space. So this is equal to w, a fixed solution, plus a constant, which I call, okay? The solution are all in the all of this this kind of all the solution are this kind of have this kind of shape. That's exactly if I make small. If you have an equation like that, y prime equal y plus b, all the solution forms an affine space. You pick one, and all the other are obtained by adding a constant. Well, that's exactly what happens here. So. And that's what happens for all the for each one of those equations. That was it happens exactly the same things. So this phi acts on the derivative of w as adding a constant, okay? And this means that the Galois group of the system of this system up here. It's a subgroup of a vector space, c to the power n plus 1, because, well, as I said, yes, I can. Do I have? Yes, I have some time. For instance, if you take some c in gal over k, then you apply it c. You compose it with phi of w. Well, this will be equal to c of w plus c0 phi. And so this is psi of w plus psi of c0 phi. So this is a constant, so it's left invariant by phi. Doesn't, okay? Does nothing, and here you have w plus the constant, plus a constant associated to phi, to psi, plus the constant associated to phi. Okay, so actually the constant, when you compose the automorphism in the Galois group, the constant keeps adding here. And I promise there's another slide, slide which is a little bit heavy to follow, and then things gets easier. So what happens if you have a solution w of tau w is equal to w plus b, which is the algebraic? So it's a solution of a differential equation. Well, it means that w and its derivative, they are algebraically dependent, because there's a. Why is that? Well, simply because it means that there's a polynomial and this belongs to this element here, algebraically dependent over k, okay? So it means that your extension n, which is equal to k plus w is not purely transcendental. It's not like it was an extension of transcendental function in the transcendence degree over k over n is small or equal to n. And so the Galois group is small. Your Galois group, which is contained in your vector space of dimension n plus 1, has a smaller dimension than n plus 1. So if you are in a vector space and things have smaller dimension, it means they are contained in a hyperplane. And so it means that your constant satisfy a linear solution. Okay, all these things are contained in an hyperplane of these vector spaces, and they satisfy a linear solution. And so you just manipulate these things. It happens that if you apply to this element here the phi of the group, it's left invariance, and you keep going. You keep manipulating things, and then you prove these things. If you're, and that's the important things, you can forget all what I've been saying, and just look at this. So if omega is a solution of an algebraic differential equation, then there exists n plus n constant, alpha 0, alpha n, and an element of your base field K, such that tau of G minus G is equal to alpha 0 plus B plus alpha 1, sorry, there's a 1 here, times delta B plus alpha n times delta n plus 1. So this was meant to give you an idea of how you prove this statement. However, once you have this statement, you can prove it in the application. And what happens for the Hölder theorem? Well, you can deduce immediately the Hölder theorems by this Hölder theorem by this statement, and that's what we're going to do. And that's very easy. So the gamma function satisfies this functional equation. So I call psi its derivative, logarithmic derivative. And then you have the psi of t plus 1. It's equal to psi of t plus 1 over t. Okay? So in this setting, you take tau to be f of t, that goes to f of t plus 1. Okay, that's your automorphism. Delta is the derivation with respect to t. And your b is 1 over t. Okay? That's exactly your b here. Okay? So what happens? When you take the derivative of 1 over t, you just get 1 over t to the power n up to some sign. So on the right-hand side, you have just a polynomial in 1 over t. So alpha 0 plus 1 over t, alpha 1 plus 1 times 1 over t square, and so on and so forth, until alpha n times 1 over t to the power n plus 1. So all your poles are at 0. Okay? Your polynomial, all these poles are at 0. On the left-hand side, you have G. G is a rational function, and you are considering G of t plus 1 minus G of t. Okay? So this is equal to something that has pole only at 0. But here it cannot happen. Why? Well, if this one has a pole at 0, this one must have a pole at some integer coordinates point. You know, they get shift up, and so you must have another pole somewhere else. So this cannot happen. Okay? This never happened, and so your gamma function cannot be solution of an algebraic differential equation. It's not differentially algebraic. So that's one thing. And so the more technical things are over. And another statement that a more general statement that you prove a little bit in the same way, using a little bit the same ingredient. If you start with this equation here, well, you may want to write it as a system here. Maybe you want to, you're curious about that. And once you have written it as a system, you have in this algebra R that we have constructed before, you have a matrix of solution of this system here, which has this shape. And Z is a solution of tau Z equal A of Z, and W is the solution of the dual functional equation with the inhomogeneous term. And it's actually a corollary of the previous theorem. So if W is solution of an algebraic differential equation, then also Z must be a solution of an algebraic differential equation. And this is proved a little bit in the same way as the previous statement. And you can turn the sentence around. If Z is differentially transcendental, so it's not a solution of an algebraic differential equation, then also W is not a solution of an algebraic differential equation. And so, if you remember what I said at the very beginning, Hölder theorem implies the fact that this Bell number generating function is differentially algebraic. How do you, I remind you the formulas because maybe you have forgotten all of it. So we have our gamma function here. So we have B of t plus 1 over t equal t B of t plus 1. And then gamma 1 over t minus 1 . Okay, so this is the homogeneous difference equation associated with the inhomogeneous equation. So what I said is not totally precise. I've been using a little bit some shortcuts which make things, well, not very precise, but I think you got the idea. So actually, you can deduce the fact that the generating series of Bell numbers is differentially transcendental over a rational function from all the Hölder theorem. As I said, it's not it's not how Clauser proves it. Clauser proves it by elementary complex analysis, which elementary doesn't mean easy, but elementary complex analysis. And so I want to conclude showing that Clauser theorem is an instance of a general behavior. Okay? So what happens in general is this: is that Clauser theorem is true in all generality. It means that if you have two rational functions a and b, and a formal Laurent power series, which is solution of a functional equation like the one that is written here. Okay? So if omega is not a rational function, then it's differentially transcendental over the field of Meromorphic function at 0 with this, where we haven't specified the radius of the disk, which are called germs of Meromorphic function at 0. And it means that this omega cannot be solution of a differential equation. So it's exactly a Clauser result in this specific case, but proof in all generality using this Galois theory. Okay. So hopefully this is a starting point to prove a more general theorem than the one I've been stating at the very beginning for general difference equation, because as I said, it's proved by recurrence. Okay, and then, well, here I've been a little bit lazy in this in this slide because I didn't want to recalculate all the rational function. This statement applies to many generating series that you can find in the literature in many different settings. I mean, they pop up in different enumerative problems. Okay, so this is a list. So x is a complex parameter. You can specify it to almost any complex number. And the polynomial you see here, this Bn of x, for instance, is defined taking the Taylor expansion of this series here on in the middle with respect to t, and you find out the coefficient here, okay? And well, here you have a tilde and b tilde, and here the functional equation is written this form. You have to work a little bit, I mean, to work a little bit around to get it in, I mean, you have to do some relatively easy computation to write it in this form, and I was too lazy to do it because in the literature the functional equations are written this way. And so to all this generating series which rise in different problem in enumerative combinatorics, you can apply the same theorem and deduce that all this generating series are not solution of an algebraic differential equation in the variable t. And just to conclude, this series gives a hint, so to say, our example of an open conjecture, which says that if you have a series an tn, sum of an tn, and you consider the series where you add this n factorial to the denominator, and if both these series are the algebraic over C of t, so if they are both solution of an algebraic differential equation, then they are both definite, and definite means that they are solution of a linear differential equation. So if these two series are solution of an algebraic differential equation, then they are solution of a linear differential equation, so they're much easier somehow in this complexity scale that I've been given at the beginning. And well, this conjecture is open, wide open, I would say, but all the series in the previous slides confirm it, so they are, I go back. Well, so you can see here all this series here. Okay, they are solution of an algebraic differential equation which is not linear, and then the generated series of the polynomial Pn are all differentially transcendental, and so they confirm this conjecture by Pak and Yelousizov. And so I think I stop here. Thank you.
Okay. Yeah. So the Clauser's result gives information about the Bn.
Yes. Well, it gives somehow, let's go back. It gives somehow an information on the complexity of the generating series, so to say. You can, well, in some way you can say that a function is more unusual or complicated if it's not solution of a differential equation. A differential equation gives you for free a whole bunch of information about the asymptotic of the coefficient, so somehow this estimate can be true, even if it's not solution of a differential equation, but there are all a bunch of information that you don't get for free. That's the idea. don't know if I cut, I answer before you finish the question.
So when you prove the Hölder's theorem, you have information on the logarithmic derivative, but
Yeah.
I didn't really get how that concluded for the gamma function.
Okay. Pardon. C'est ici. Okay, what I'm saying is that I focused on this relation here, okay? So what I said is that B, it's equal to 1 over t, so, and delta is equal d over dt. In this specific case, tau is sense f in f of t plus 1. And so what happens is that when you take the derivative of d, di of b, this is equal to, hopefully I get the wrong sign. Okay, this is equal to, the derivative is like that. So you have a rational function, g of t plus 1 minus g of t equal to alpha 0 over t plus alpha 1 over t square plus alpha n over t n plus 1. Okay? So all the poles here are at 0, but here there must be another pole, because if the 0 pole is suppose that is g of t that has a pole at 0, this other here must have a pole somewhere else over z. Okay? And so this cannot happen. Never. This never happened. And so gamma is not the algebraic. Okay? Because we said that if the solution is the algebraic, then you can find an expression like that. So since you cannot find this expression, the gamma function is not the algebraic, so it's not solution of a differential equation.
Bah, j'ai peut-être pas bien compris, mais vous l'appliquez à la dérivée logarithmique, ça?
Oui.
Mais c'est la dérivée logarithmique qui est pas...
Ah, okay. D'accord. Well, if you have a polynomial which is gamma prime, gamma over gamma prime, so gamma so you get the logarithmic derivative verify a differential equation like that, but you can algebraically you can clear the denominators and get a nonlinear differential equation for gamma. Okay? Sorry.